Dear viewers, welcome back to our end-to-end demo of the autonomous driving functionality development. In this series, we are demonstrating the entire AD software development cycle, from customers' requirements to the approval for release in the target vehicle. We also describe the challenges encountered on the journey to the software-defined vehicle. The audience we are addressing are predominantly technical people, but also managers working in the area of autonomous driving. Most topics covered in this series are also applicable to other vehicle domains. In this session, I will present the three most important strategies for reducing the risk and cost of the software development for software-defined vehicles, or SDVs for short. The first strategy I'll mention is the reuse. Next, I'll explain the importance of the early cross-domain testing. The last strategy described is based on automation. Finally, I'll show how all of these strategies can be unified with the concept of a software factory. The first strategy I'd like to present here is the reuse. Reusing already developed assets obviously reduces the development time. In addition, any assets that have previously been used and tested are likely to contain less defects than newly developed ones. Finally, substantial portions of safety verifications performed on a system can be transferred to new products when parts of the system are reused. Reuse therefore creates significant opportunities for both cost and risk reduction and should be exploited wherever possible. Nowadays, many components are already shared between different vehicle models and their variants in the same generation. In addition to that, more advanced reuse scenarios can also include reuse of software components across vehicle generations. This can be helpful even if it is used just to bootstrap new software development in a fully functioning environment. Reuse of code is also imaginable across user functions, if on the architectural level the software is built from small, reusable components, as illustrated in the right-hand side of this slide. In that case, components like eco-motion estimator and a camera-based perception might be used to implement the autonomous emergency braking ADAS function. If augmented by object classification and lane marking detection components, further functions like adaptive cruise control and lane keeping assist can be built with a significantly reduced total effort. Finally, large time saving are possible by reusing the results of a functional safety and safety of the intended functionality analysis and verification, especially if the system is designed using model-based system and software engineering principles. We have previously seen that in order to make a SDV project manageable, individual vehicle domains and larger user functions are developed separately from each other. Most often, their integration only begins after the target ECUs become available. This typically happens in late stages of the project and in limited quantities. As a consequence, there is not enough time left to fix all software defects found at this stage before the planned start of production. To avoid such an outcome, we propose the early cross-domain testing strategy leveraging software in the loop testing. This approach requires a central testing strategy to be defined and agreed on with the participants delivering software, which will be part of the software under test. It precisely specifies which kind of tests need to be performed, and also how and when. The tests should be automated as much and start as early as practically possible. Special attention should be paid to the cross-domain verification, as this is the key problem we are trying to solve. Testing should be as extensive as possible, which requires large amounts of input data and also produces a large amount of results. Test data management is therefore also a critical part of the central testing strategy. As a part of the testing strategy, typically a centralized software repository will be introduced. To facilitate automated software integration, all suppliers for all domains should deliver their artifacts to this repository in a uniform format and according to standardized set of rules. The software from this repository will then in regular intervals be integrated on a dedicated integration and testing platform. At the beginning, this platform may only execute software-in-the-loop tests with pre-recorded inputs. With time, it can evolve towards processor-in-the-loop tests and a simulated environment. In all cases, the completely integrated software should be tested from end to end, and for all possible software configurations. Once the actual target hardware becomes available in sufficient quantities, further software testing can be performed on hardware in the loop platforms. By that time, the number of remaining software defects should be low enough to enable timely project completion. Currently, no large-scale software development can be completed without involvement of a very significant number of human developers. They are the essential driving force in the project, but as we all know, humans are prone to occasional mistakes and are also an expensive and limited resource. Especially this last aspect is a considerable obstacle for projects that require rapid scaling to a large number of qualified developers. In contrast, automated systems are cheap, reliable, and most importantly, highly scalable. They are ideally suited for executing relatively simple, predictable, and repeating tasks. Given these clear advantages of automation, it should be applied wherever possible. However, there might be a relatively large entry barrier for automation, due to high initial setup cost and time needed to implement more sophisticated automated solutions. But if an automated system is used long enough, this initial investment will be offset by cost and time savings over the years of usage. As an example, I will show how the automation strategy should work in the context of the previously mentioned early testing strategy. A fully automated testing system would take over the code after it was written and reviewed by human developers. It would then automatically perform comprehensive testing, including automated builds of varying software configurations and their testing in cloud-based simulators and hardware emulators. Also, the test results should be automatically aggregated and presented by a central reporting platform. The implementation of such extensive automated build and testing platform clearly requires a significant amount of time and resources. Very often, this effort will not be justifiable for short-term projects. A longer time horizon becomes available if we transition from discrete software projects to continuous software production. In that case, software development can be viewed as a gradual process, smoothly evolving over multiple product generations. With the extended time horizon, we can afford to develop generic, modular software components which can be reused in many different configurations. Robust automated processes for software configuration, builds, and all levels of testing. Central testing strategy, artifact repositories, and test environments, which will enable testing of entire software systems even before the target hardware becomes available. With these steps, we can create a software factory, a highly automated platform for development, testing, and deployment of software systems. In the previous session, I have outlined the challenges related to software development for SDVs. In this session, I have shown how these challenges can be overcome by software and documentation reuse, process automation, and early end-to-end testing. Ideally, all these strategies will be employed together in the form of a software factory, which is our recipe for reducing the gap between the demand and the capabilities in software development for SDVs. Subsequent videos in this series will demonstrate practical solutions for implementing these strategies. Among other topics, we will show a demo of a highly scalable containerized development environment and take a deep dive into model-based software engineering. Please check the description section below for the links to related videos in this series. Don't forget to subscribe to get notified when we publish a new video in this series. We always appreciate your feedback. If you liked this video, please press the like button. You can also leave your comment below or get in touch with us using the contact form on our homepage. Thank you for watching.